I've been listening to a lot of classical. Hey, am I live? I must be live right now because I hit the live button, but I can't see myself. So I always have to wait like 15 seconds or so. There I am. Okay, great. Great. Hello, world. It's Siraj. How's it going? So today we are here live and we are going to make some word vectors out of a series of books called Game of Thrones. If you know Game of Thrones, give it a shout out in the comments. Let's see who knows what this is. It doesn't matter if you don't. The point is we are learning about the concept of word vectors, and we want to take some books and make them into vectors. And once we have these vectors, we're going to do a bunch of really cool stuff with it. All right. So who's in the house? Let me name some names. We got Jake, Akash, Party, Taher, Teddy, Reki, Party, Ricardo, Angel. Got a lot of people in the house. All right. So, okay, let's go ahead and do a 5-minute Q&A, and then we're going to get into the code. It's going to be an IPython notebook, and I'm going to give you guys the data set as well. So 5-minute Q&A, let's get started. Glove or word2vec? We're using word2vec, not glove. Although glove is similar. Also, I haven't used glove before, but I've heard good things. Another question. Best character in Game of Thrones? To be honest, I don't even read Game of Thrones. I just picked it because I think the idea is cool. I don't have time to read anything or watch TV shows anymore. I'm just focused on content. Any maths? We are going to do, yes, we're going to do some maths. We're going to use the cosine similarity as a measure of distance between word vectors. It's a corpus, yes, it's 5 different books, but we're going to treat it as one big corpus. Please say my name, Piyush. Okay, okay, doing the deep learning foundation and feeling utterly lost. Keep pushing through or go back to school. Okay, guys, listen. Okay, so clearly there's a lot of stuff in deep learning, and there's a lot of math. And from what I've read, I have taken your feedback into consideration. We need to really dive into the math. And we're going to go so deep into the math in the next video, okay? So the next weekly video, get ready. We are going to really dive into the math. Please say my name, Colin. What's a word vector? I'll explain that in a second. Clean the camera, there's moisture. Okay. Okay. Video isn't clear, bro. Okay, can't help that right now. Is OpenAI worth to explore? Yes. 1-minute rap before this. I love your rap. I'll do that. Yeah, I'll do that. Let me answer some more questions. How can I classify images from a live feed and put the output in a file? From a live feed, you'd want to, oh man, in a live feed, well, we know how to do it recorded, but in a live feed, you'd want a live classifier to look at your screen, or maybe segment the screen. So you'd want to use probably JavaScript for that. JavaScript would be easy. Convnet.js, Andre Karpathy's library would be great for that. The cam looks dirty. Hey man, I was just at the beach recording some cool stuff. Predict who dies using word vectors, that's gonna be possible. Are you gonna use TensorFlow for this? No, we're going to use word2vec, and we're gonna use a bunch of other smaller libraries. All right. Okay, so one more question, and then we're gonna get started. Okay, here we go. If we increase vocab size by adding words, will that help? Yes, yes, it helps. It helps if it helps if the words are relevant to the problem we're trying to solve. If they're relevant to the story, which is Game of Thrones in this case. Okay, so that's it for the questions. Let's get started with this. I'm going to start screen sharing. It's going to be an IPython notebook, and then we're going to. Oh, that's right, a wrap. Let's do a little wrap for a second. Let me do a wrap on vectors. Vectors, right? Okay, so start the tutorial with the wrap. Okay, here we go. A wrap about vectors. I do it, man, because I'm Victor. Victor, vector. What's a vector? Victor. I'm on a plane going crashing down like my mind is a scalar. Scalar clouds going down. Scalar clouds going up. I see 1, 2, 3 in the sky, and it's my enemy. No, it's not. It's just mine. And I'm going to fly back to the screen. So here we go. That was it for the rap. And let's get started because we are getting serious, guys. This is all about word effect. Yes, it's in English. Favorite movie, The Matrix. The Matrix. How about that? I'm just going to add to the list of people who said The Matrix. Let's get started. This is an NLP session. We're going to do some natural language processing. Ready? Okay, let's start screen sharing. Let's start screen sharing. Okay. Okay, let me move you guys over here. Okay. All right, so let's get started with this. Let me make sure that this is showing. Hold on. Okay, so we want to, let me just first say, we want to, the goal is to create word vectors from Game of Thrones data set. Now, look, guys, these are just the 5 books. Let me show you guys. I'll just show you guys and play with them and analyze them to see semantic similarity. Okay, let's look at what we've got here. So, hold on. I can even show you guys the data set for a second. So these are just the 5 books for Game of Thrones. Okay, there's literally just the text files for the books. They are these huge text files for the books. That's all they are. Okay, and I just took 5 of them. I downloaded them from Pirate Bay. No regrets. You know what I'm saying? So that's what this is, and that's it. We've just got 5 books in the series. We're going to take all these books and we're going to create word vectors from them. We're going to treat it as one big corpus. Okay. So that's what we're going to do. So let's just go dive right into this baby. All right. So the first thing we want to do is we want to import our dependencies. Now, we've actually got a lot of dependencies for this. So I'm going to explain every single one. So the first one we want to do is import future. And why do we want to import future? Can anyone tell me why in the comments as I type this? The reason we want to import future is because it's the missing link between Python 2 and Python 3. It allows us to use the syntax from both. It's kind of like a bridge between the 2 languages. And we're going to import 3 functions that we're going to use for this. Okay, so that's the first step. Once we have that, we want to we're gonna encode our words. So we're gonna for word encoding. How are we gonna encode our words? Well, we're going to use codecs. The next one is we're going to perform some regex, and regex is basically whenever we want to like search some file really fast. That's all about regex. It's a way of like quickly and efficiently searching through a large text or number database for what you need. The next one is for logging. So actually, we don't need it. We don't need to log. Oh, now I actually haven't talked about concurrency before, so this is going to be interesting. We're going to import this multiprocessing library to perform concurrency. And if you don't know, concurrency is a way of running multiple threads and having each thread run a different process. So it's multi-threading, multi-processing. It's a way of moving. It's a way of having your program run faster. Okay, and I haven't talked about this before, but we're going to do this a lot in the future, especially when we get to distributed machine learning, which is later on in this course. Okay, so that's it for multiprocessing. The next one is dealing with the operating system. Like we want to reading a file, and for that we'll want to use the OS module, and then we want to do some pretty printing, make it human readable. And how do we do that? We're going to import pretty print, pprint for short. Okay. The next one is more regular expression. So glob was, and I'll show you guys a difference here, but this is for a more granular regular expressions. So this is like step 1, by the way. This is like step 0, import our dependencies. And I've got a few more, and then we're going to get started with the actual logic of the code. Okay. So what else do we got? We got the natural language toolkit because we're going to be using NLTK. Okay, natural language toolkit. Let me show you guys NLTK for a second. If you don't know, now you know. Let me show you guys NLTK, because NLTK, and I made videos about this before, is the shit. Okay, NLTK is awesome. It is so easy to use. Let me zoom in on this thing. Okay, literally, it can tokenize sentences in single lines of code. So if you have a sentence like, at 8 o'clock on Thursday morning, Arthur didn't feel very good, you feed that to NLTK, and boom, it'll give you the tokens for each word. Why is this useful? Well, you can have part of speech tagging, POS tagging, which means like, oh, is this a noun? Is this a verb? Is this a CD? How does it know these things? Because it has a pre-trained, well, it's actually two things. It's for some of it, it's got a pre-trained model which it trained, and another part of NLTK is it's using the which I talked about in the last video, which is the like having that database of pre-recorded sentiments, the lexicon. That's the word I'm looking for. All right, so then we're gonna use Word2Vec. Now, Word2Vec is the shit. That is what we are going to use. That is the real meat of this code, and I'm gonna really deep dive into what Word2Vec is. At a high level right now, Word2Vec is what Google created to basically, they trained a neural network on a huge data set of word vectors, and it created vectors, and we can use these vectors in other ways. So it's like a generalized collection of word vectors. Okay, so I'm going to talk about all this in a second. Let me just keep typing out these dependencies. The next one is dimensionality reduction. Once we have our word vectors, they're going to be multidimensional. They're going to be 300 plus dimension word vectors, okay, because they're so generalized. And we want to plot them on a 2D graph so we can see them. And how are we going to do that? Well, we're going to perform a technique called dimensionality reduction. I have a video on this called Visualize Data Set Easily. Check it out. Check it out. Okay. Now, so then we're going to import our math library, which is NumPy, and then we're going to import our plotting library, which is going to be matplotlib. And finally, we're going to what's the next one? Parts of data set. We got one more after this. So many libraries, but yo, it's important because right now we're talking. We want to talk about the concepts here, and we're going to dive into these specific processes later on. Okay, so import pandas as PD, and lastly, here's the last one: visualization. Seaborn. Seaborn is going to help us visualize our data set. Okay, as SNS. Okay, that's it for our dependencies. Boom. All right. So okay, so now that we've done that. We're not using pre-trained word vectors. We are using word vectors that we train in real time. Let's see. No model named Plylot. Oh, PyPlot. No model named Pandas. Oh, Pandas. See, this is why I love IPython notebooks. Okay, so so that was that. Now our next step is to process our data. Okay, so step one is to process our data. What does this look like? Well, before we do anything, we want to clean our data. So how do we clean our data? Well, NLTK has a really handy function for this. Well, the first one is called punct, and the next one is called stop word. So what does this do? What this does is it downloads, punct downloads, it's a tokenizer. It's a pre-trained tokenizer. It's a pre-trained tokenizer, and what it's going to let us do is tokenize our text. Now remember, I talked about tokenization last time. Tokenization is where we take a sentence or a word, and we take a piece of text and we split it into tokens. And those tokens can be sentences or words or even characters. It's whatever we specify. In this case, we're going to do sentences. Okay, so that's what punct does. And stop words are words like and, and the, and a, of words that don't really matter. They don't really have a lot of semantic meaning. And we want to remove these words. And why do we want to do that? So that our vectors that we create are more accurate. Okay? So we've done that, and it's going to download. Okay, and it says, okay, you've already got them. If we don't have them, it's going to download it. The next step is to get the book names, matching the text file. And now, like I said, we had them right here. So let me make this bigger. Here's our books right here. So they end in text file. So we can just say, okay, so get the book file names, and before we use glob, glob is going to let us get those books that just have that end in .txt, right? And it's going to print those out for us. Make sure that we actually actually printed them. All right. And it ends there, and it starts here. Okay. Boom, boom. Okay. No. There we go. Okay. So that's for our text file, and let me print out the books. Let's print them out. Let's print them out and make sure that we got them. File names. Sorted glob.glob. Let's see what we got here. .txt. Let's see. So we should have them here. And if we don't, then the problem is that we, hold on, sorted glob.glob. Let's see the hold on a second. So let's see. Interesting. So what this is let's see. Okay. So okay. So it seems like they might be in the root. Yeah, they might be in the root. 1 second. And what I can say is, hold on a second. Open closing folder. Hold on a second. This is actually not. Oh, you're right. What are people saying? /. Okay, hold on a second. Oh my God, some of people are saying some shit. Hold on. Okay, so okay. Invalid syntax. So let's get that current directory. I swear to God, this is so annoying right now. Hold on. Okay. Okay, so hold on a second. Okay, so oh my God. Okay. File names. Invalid syntax, book file names. What are you talking about? I just named them right here. Let's see, book file names. Hold on a second. Hold on. Invalid syntax. Hold on. So we really don't have time for errors like this. Oh my God. I should have talked. Okay. Okay, guys. So I actually had a comment with a lot of upvotes, and the comment was we should just not spend time actually writing out the code and just show the code since I'm already reading off of it anyway. So I already have the code anyway. So why don't I just show you guys the code, and I'm going to explain it as we go, okay? It's because seriously, I don't have time to look at why this is not working right now. print book file names. That's exactly what it was. Okay, so we don't have time for this. Okay, so let's just talk about this. Okay, let me move this over here. Okay. And I've got my notes here as well. Okay, hold on a second. So, okay. So where were we? Let me see if this actually works. MLCK. Why the fuck? Hold on. Let me just restart this whole IPython notebook and run this from scratch. Okay, let's run it from scratch. IPython notebook, and let me close out everything. And okay, so here we go. Hold on, that was I missed Python notebook. Boom. Okay, so let's see. Let's have it give it to us. Okay, and we'll try out this one. Okay, so let's just run what we have here. PyLab inline, populating, log. Boom. Okay. File names. Okay, so clearly clearly we're having a problem right now. And the point is, let's just, okay, so this is pre-compiled anyway, and I talk about what this is doing, and we're going to really deep dive into the important concepts here. Okay, so we're going to keep going onwards. We don't have time to stop with this right now. So, okay, so we've got our book file names, right? And next step is to combine the books into one string. And why do we want to do this? Because we want to have one corpus for all of those books, and that's what this does. We initialize a raw corpus. We say U. Let me make this bigger because we really want to. We start with U because it's Unicode, right? It's a Unicode string, and we want to convert it into a format that we can read easily. And what is that format? UTF-8, right here, okay? So UTF-8. So this is where the codex library comes into play. We are using a codex library to read in the book file name and convert it into UTF-8 format. Now, remember that corpus raw function we just initialized up here? Well, now we want to add all of the books that we see to that corpus. And the way we're going to do that is we're going to add it all to this corpus raw, and at the end of it, it's going to have all of those books in one variable in memory, corpus raw, okay, which is going to be a very, very, very big variable, okay. That's what we're going to do, and so that's the first step. And once we have that, then we're going to split the corpus into sentences. Now, remember when I said we downloaded that punct model right up here? Let me show you guys. nltk.download punct. Well, now we're going to actually load that into memory. It's a trained model, and it's loaded it's in a byte stream, and that's what Pickle is. It's that file format that we can load as a byte stream. Now, that's what that does, and it's going to load it up into this tokenizer variable. This tokenizer is pre-trained. It turns words into tokens, and the type of tokens we want are sentences in our case, right? So we'll use a tokenizer. To tokenize that corpus, which is every single word we have, right? And let me open this. So every single word we have, and this could be anything, guys. This could be any piece of text you want, any book, anything you download, any big piece of text. The same principles apply, okay? And we're gonna put those all into this raw sentences variable. Once we have that raw sentences variable, we're going to convert it into a word list. So what do I mean by a word list? Well, I also, hold on a second. Make sure. So for our word list, we want a list of words, but right? But what exactly do I mean by that? Let me so for our word list, let me see the comments. What are you guys up to? Okay, so this is okay. So let me comment this as well. So we want to convert into a list of words. Remove unnecessary characters. We want to remove unnecessary characters. That's why we have that A to Z. We want to split into words, no hyphens, you know, and it's going to be a list of words. So that's an array. So it's a list of words. Okay. Once we have that list of words, for each sentence, we're going to take those words and tokenize it. So it's going to be a sentence where each word sentence where each word is tokenized. That's what this does. So for every sentence that we have, we're going to initialize an empty sentence list. We're going to add it. We're going to add sentences to it, and then once we have that, all right. So I've got some comments that I should slow down a little bit. I can do that. I can do that. Okay. So let me slow down a little bit. There's so much I'm trying to cover. So I'll slow down. Okay. So we have a list of words. Each word is tokenized. Okay. Each list of words is considered a sentence, and we can see that when we print it out. So we have our raw sentence, which is, he was an old man past 50. He's seen as the lordlings come and go. This is a sentence taken directly from Game of Thrones, and it's at the 5th index. So if because we combine all of our books in order, this is going to be the 5th sentence in the first book because it's one big corpus. Okay, and once we have that, we're going to convert it into a word list, which is tokens. And see these U characters, they basically help us convert them into their Unicode representations, right? So whenever we're dealing with words, any kind of text, we have to make sure it's in the right format. And Unicode is that format we want for vectors, okay? And UTF-8 is that format for reading from files. So once we have our big book corpus, let's print out how many tokens we have, okay? And each sentence is, and what we're going to do is we're going to consider each sentence a token, and we can print out. There's 1,810,000 tokens. Okay, so no, we're going to get into vectors. I'm going to explain vectors in a second in detail. We haven't gotten to that part. Okay, so that's what we've just done. Now we're going to train word2vec. Okay, these are our hyperparameters. Let's talk about vectors for a second. Like word. Okay, so I'm sure I can find a great image for this in a second. So word embeddings are here. So TensorFlow probably has a great image for this. So, okay, so here's a great one. Here's a great one. Copy image address. Let's blow this image up. Let's get it really big. Okay, so here are vectors, for example. So look at the one on the left, okay? Look at the one on the left, king, man, woman, queen. These are word vectors. So when we have a set of words, okay, we have a set of words like, so let's say, masculine, John, Bob, Sergey, like words that are like men, right? So words that all have the same semantic similarity. We can generalize all these words into a vector representation. We also call them word embeddings. So there's a lot of terms here, but we want to make sure that it's all really the same things. We don't want to be confused. Word embeddings, word vectors, same thing. So if we have a set of words, we can generalize them into man. Okay, so that's what man is. Okay, so man, woman, king, queen. These are generalized vector representations that we have created after training on a very large corpus of text. Okay, so when we have a new word, like we say, like, what's something manly? I mean, this is right now. This is a gender landmine. I mean, this example, but let's pick an example like, what do men have that women don't? This is like, right? So a penis, right? That's the only thing I can think of that's like literally true and doesn't cross any kind of other things. So penis, right? So penis would then, if we were to feed it to a trained word2vec model, it would see that penis is closest to man. Okay, why does it know this? Because it's trained on a corpus of text to eventually find the similarity, that generalized representation across all of these words. And how does it do this? Well, it converts words into vectors, and then it creates vectors of vectors. And these vectors are, when we plot them out, we can see how similar different things are. Yeah, beard was a great one as well. Okay, so balls, okay, because it's attached, right? And so then once we have these vectors, we can see what's similar to them, right? We can do all sorts of things. Mainly, there are 3 things we want to do, okay? Let me write this down. Let me write this down. So write this down. This is very important. So once we have vectors, 3 main tasks. There are 3 main tasks tasks that are, some women have beards. So 3 main tasks that vectors help with. Okay, here are the 3 main tasks. One of them is distance. Okay, hold on. Distance, similarity, and ranking. Okay, so those are generally what they help us with. And what do I mean by that? Similarity, like so vectors are good for things like if we want to think about any kind of what's the word I'm looking for? Like if you want to see how similar 2 words are, which we're going to do later on. If we want to rank something, right? So if we wanted to browse all the scientific papers in the world, we'll create vectors out of all of them. And then we want to rank them in terms of some metric that we decide, like what's the one that has the most information on, say, climate change. We could then rank them semantically. So it would say, here's the #1 paper that has the most verb usage or word usage about the topic climate change, and it uses vectors for that. Okay, these are really useful. Okay, so let's go ahead and talk about these hyperparameters. So num features is a dimensionality of these word vectors. Okay, so number of features is the dimensionality, and we say 300 because we say 300 because we could say 400, we could say 500. The more dimensions, the more dimensions, the more complex, so more computationally complex, expensive to train, but also more accurate. Okay, so the more dimensions a vector has, the more generalized. More dimensions means more generalized. Okay, so we're gonna say 300 for now. Okay, minimum word count threshold is what is the smallest set of words that we want to recognize, okay, when we convert to a vector. The number of threads to run in parallel, so if we are, so what is the actual structure of a vector? That's a great question. The structure of a vector is, so the definition of a vector, and we're going to talk about this in the next video, but we're going to really deep dive into it later. But the definition of a vector is it's a set of numbers, okay? And in this context, in machine learning, in physics, it's got a different context. We talk about it talks about a direction. In our case, we're just talking about a set of numbers. So we could think of it as a list, a huge list of numbers. Okay, that's kind of what it's represented as. Okay, so and in TensorFlow we use the word tensor because a tensor is an n-dimensional array of numbers. So a vector is a type of tensor. So vector is a type of tensor. So this doesn't really belong here. I'm just saying this right now. Vector is a type of tensor. Okay, so then the number of threads to run in parallel. This is where that multiprocessing library that we imported comes into play. Okay, we want to say how many workers do we have. So the more we have, the faster our model train. More workers, faster we train. Context window length is the size of what we're looking at a time. Like the size of, like if we think of it as like looking at blocks of 7 words at a time, that's the context window. Downsample setting for frequent words is hold on. Scalar, vector, matrix, tensor. Exactly. We're going to be talking about those in the next video. But downsample settings for frequent words is once our trained word2vec model is noticing a lot of frequent words, we don't want to have to look at them constantly. So any number between 0 and 1e-5 is good for this. So that's generally that's what we found is a good that's generally a good use case for this. But basically, how often do we want to look at the same word? The more frequent a word is, the less we want to use it to create vectors because it's already a part of our trained model. So then the seed is for the random number generator, right? So that's what that is, random number generator. And why do we use a random number generator? We use it to pick what part of the text we're going to look at to turn into vectors. Okay, and the seed makes sure that it's deterministic. This is good for debugging. Deterministic, good for debugging. Okay, so this is our actual model right here. a word2vec model we imported from the GenSim library. And let me show you guys GenSim for a second. GenSim is super useful. It's for topic modeling. Basically, you give it any kind of corpus like this, it'll create a model, it'll train it, you can save it, you can load it later on, and then given some words like woman and king, something that was in the actual corpus, it'll give you words like, it'll give you things like how similar they are, what doesn't match, give you the straight up vector so you could use it later on. GenSim's a great library, okay? So that's going to actually train our model. And this is going to take, since our model is relatively small in the context of deep learning, this is only going to take 30 seconds or so to train, okay? All right, so, and it's actually not the same definition as in physics, and there's a lot of debate about this, actually. I've been looking at a lot of Stack Overflow answers and a lot of Quora answers, and it's crazy how much people are debating over these words in machine learning. But the point is, it's just numbers. It's number representations that we create, and then we can feed into our model, okay? So then we're going to build our vocabulary, and so then we're going to build our vocabulary using those sentences, okay? This is how we actually, this is how we load the corpus into memory. We haven't actually trained it. We built our model, right? This is step 3, build our model, but which I should have written up here. So step 3 is build model. Build model, okay? So once we built our model, we have loaded our corpus that we cleaned into memory, and we printed out the size of it. Now we can start training. And it's going to train on all of those sentences we gave it. It's going to take 30 or 40 seconds. And when it's done training, we're going to save the file for use later on, okay? And easily do that using that OS module. Great for that. We can save it, and we can save it, and then we can load it later on. In fact, we can load it right now. We'll load it from memory right now, okay? And once we have that, we're going to compress those. Okay, so that's going to be 300 dimensional word vectors once it's trained. So in this Thrones2Vec model right here that we've trained, it's going to contain all of those word vectors that we just trained. Everything is in memory right here. But these are 300 dimensional word vectors, okay? We cannot map a 300 dimensional word vector on a plot for us puny humans to see. How are we going to do that? Well, we're going to use a method called TSNE, which stands for T-Stochastic Distributed Neighbor Embedding. Okay, and I have a great video on that. Basically, let me just. It's an awesome technique. This is not useful, but basically, I have a great video on that. Let me just type the video name for that. PCA is another. My video, it's called, what's it called? How to visualize a data set easily. I really dive into this method right here. How to visualize a data set easily. But in a nutshell, TSNE takes our 300-dimensional vector and squashes it into just 2 dimensions. Why? So that we can then plot it and view it. How does it do this? It's actually a long explanation, and the video is great for that 5-minute explanation. Definitely check it out, okay? Right, so so that's what TSNE does. It's going to create those vectors, and so it's going to squash it, okay? And we're going to take all those vectors and put them in one gigantic matrix, right? We've initialized TSNE here, but we haven't trained TSNE, right? So TSNE is a model. It's a machine learning model, and we have to train it, okay? So we'll train it on that word vector matrix, and this is going to take a minute or 2, like it says. And so it's going to create this word vector. It's a 2D matrix, right? So this is one gigantic matrix, and it's got the plots on the points with it. Okay, so then we're going to plot what we've got, okay? So what do I mean by plot? Well, we want to plot it in 2D space. So for every word we have in that vocab, we want to have 3 columns: the word, the x coordinate, and the y coordinate. Now, how does it get these coordinates? Well, that's what TSNE does. Not only does it not only is it so it's squashing these vectors into two-dimensional vectors, but it's also giving us the x and y coordinates of those vectors in two-dimensional space. Okay, so these are all words from that corpus, right? These are all Game of Thronesy words, right? So that's what that does. And once we've got that, then we're going to plot them on a graph. So this is where Matplotlib comes into play, right? We're going to plot these points, and we're going to plot them on a graph, and it's a lot. These are our word vectors. There's a lot of them here, right? And we've brought it down to scale so we could see a lot of them. But all of our word vectors or word embeddings, whatever you want to call them, are here in 2D space. Now, what are we going to do with them? Well, we can see what vectors are close to each other. Let's start with that. Let's see what vectors are close to each other and what that tells us about the data, okay? So the first thing we want to do is zoom in on this, right? And that's what this function does. It creates a bounding box of x and y coordinates in that graph that we have, and it shows just that bounding box. That's what this function does, okay? And so then we'll use that we'll say, okay, so in the bounds of this, in the xy bounds of these coordinates that we give it, let's see what it gives us. This is what it gives us when we look in this corner. Well, what are all these? These are names: Baristan, Gregor, Clegon, Sandor. These are all names, and they look like male names as well, right? They look pretty much male. Okay, so interesting. Just by training vectors on our model, it created just by training and creating vectors and plotting them in a two-dimensional graph using TSNE, I removed stop words and special characters. Stop words was included in that list, at least in NLTK. But it shows that these words are all close to each other because it knows that the distance between these words, it's small, so it graphs them very close to each other. So it's pretty cool, right? So if we look at a different region, if we look at a different region, we'll see that, hey, this is food, right? This is a totally different region. Pepper, pickled, cod, olives, turnips. These are all similar words. And I want to really stress the importance, the brevity of vectors, okay? Not the brevity, the wrong word vector. The enormous awesomeness of vectors. Okay, word clusters are related. There's so much we can do with this in every field, in legal, in law. We can train an AI judge using this thing, using semantic similarity to see the differences between the different case data. We could see what's similar. We could use this to find new drugs. Like what is the semantic? What is the cosine similarity, or what is some similarity metrics that we define between a corpus of scientific papers on some problem that we're trying to solve. So this most similar function is already created for us. But basically, we'll say, well, we'll give it Stark, and then it'll show the similarity by a number. So it'll rank them. All of these names are similar to Stark, right? And how are we doing this? Well, there's a lot of methods for measuring semantic similarity. There's a lot of methods for measuring the similarity between vectors, and the one we're using here is the cosine similarity. So let me bring that up. The cosine similarity. The cosine similarity, impossible distance metric we can use, because turning these words into vectors, turning our videos into vectors, turning our images into vectors gives us a way to mathematically reason about these things. We can reason about them just like we reason about numbers in a mathematical way, right? So so this is the formula for the cosine similarity, right? So given two vectors, we can use the dot product and the magnitude of those vectors to calculate them. Okay? So that's one method. There's a lot. There's like the Haussian, I think it's called like the Haussian similarity. Like that, or the Gaussian, no, of course the Gaussian similarity, but it's like anyway. there's a lot, and I'll link to more in a different time. So anyway, so then we'll use that to say, okay, so given these three words, Stark, Winterfell, and Riverrun, it'll say, well, Stark is related to Winterfell as X is related to Riverrun. And what is X? And that's what this does. It says, okay, so it's going to measure the similarity between the first two parameters we give it. And then it's going to say, for that similarity, be that like 0.5 or 0.6 and 0.7, what is something that similar to that last parameter, Riverrun? And it'll find that from our list of existing vectors. And in that case, in our case, it'll be Thule, Tyrion, Dany, things like that, okay? Okay, so there's that. That's the end of this already. And I because I didn't type out the code, it went a little faster. Yeah, so let's wait, where's my screen here? Let me stop screen sharing and go back to this. Oh man, okay. Hi guys. Let's do our ending 5-minute Q&A, and then we're going to end this live stream. Okay? I have an awesome video coming out for you guys. So I've been working really hard to thank you, Sangram. I really appreciate it. I'm really excited about this next video. I'm using a MacBook. Thanks, Vocalize. What else? Thanks, Barty. Can you please elaborate on how is the projection of each word of each work to the coordinate work to the coordinate? What do you mean? What are real life applications of this? Great questions. Thanks, Xerox. Okay, real life applications of word vectors. Take any piece of text. Take a book. Okay, after this live stream, download a book. Okay, download an ebook and convert it to a text format, and then use the code that I give you. And you can easily feed it to Word2Vec and create vectors. What do you do with these vectors? Well, then you can, besides the similarity and the distance, what's a good application for vector? Like download a corpus of what your friends are saying. You can see what you can rank personalities, like chats, like this guy's chats versus this guy's chat, or this guy's what he said in a speech versus what he said. If you want to compare Hitler to Trump, I just went political. Not trying to go political anyway, but I just did. If you want to compare anything, word vectors are good for that. Ranking. Words are everywhere, guys. Any kind of similarity or ranking, that's what it's for. And there's a lot of possibilities. Okay, so how are the words assembled into vectors? Is it just context? Are there any ontological network being built? If so, how? Right. So when Google released Word2Vec, okay, so it trained a neural network on these vectors, and these are labeled. It was a labeled corpus of words, and well, actually we could do this unsupervised as well. But basically, we convert words to vectors, and single words to vectors, and so that gives us a number like 0.8 or 0.9. And once we have those vectors, then we could create even more generalized vectors by looking at the similarity. And the similarity could be like, this is 0.9999 and this is 0.9998, and these are very similar. Okay, so and that creates even more generalized vectors. Okay, so anyway, guys, I've got to go. I've got some editing to do, some shooting to do, some Udacity talking to do. And I love you guys. We're gonna next live stream is gonna be much more, dope. And not that this one wasn't. They're all dope. I'm dope. You guys are dope. We're all dope. Okay. So for now, I gotta go take a chill pill. So thanks for watching. Love you guys.